Hello guys, so this is our Thursday lecture, although it's Sunday already. So first, sorry for this delay, but okay. So we're gonna talk today about the timers, and we're gonna start with the simplest timer in our microcontroller or our robot kit microcontroller, which is called Systick Timer or System Timer. It's a very simple one. Okay, we're gonna use it in two simple applications. To how to measure a delay, for example, and to create delay, and finally to control the speed of the motor, as we're gonna see tomorrow on Monday. Okay, so let's talk about this guy. So again, we're gonna use the slides from TI, their course there. This is actually module 9. Okay, so let's go and check our, yeah, this is module 9. It's called, as you see here, the Systick Timer. Okay, so basically we're gonna talk about the precision of this timer. Okay, the range, how much time you can actually count there, and the resolution. Okay, and of course some application for it. Good. So let's start here. So basically, this timer, okay, has 3 registers. One of them is called load register. This guy is a load register. And the other one is called value. And there is another one. Okay, we're gonna see maybe after 2 slides or something, to control or configure the Systick timer. So basically, you put a value in this load, some value, and then when you start the timer will start from this value. So if this value, for example, is n, it will count down until it reaches 0. And the current value of the timer, of the counting, which is counting down, will be loaded to value register. So this is the current count of the timer. If it's 0, then we reach the end. We counted from n, actually n minus 1, as we will see later, but let's call it n for now, n to 0. Okay? Of course, this will create delays. So if for some application, and we will see, more and more in the future lectures, we needed some sort of delays. So instead of doing this, very dumb way of creating delays, which is unmeasurable, we can say, which is the for loop, the dummy for loop that we always use. Okay, we're gonna use timers because they are giving us some precise value for the delay. Okay. So this is some, some of the basic highlights for this timer. So how it works, as I said, there is 24-bit down counter that decrement with the bus clock frequency. Whatever, as we will see later in this course, we can change the frequency of the microcontroller, the clock frequency. Okay, so Systick is tied to the clock frequency of the microcontroller. So when it starts by n, then it count down to n minus 1. This will take 1 clock cycle. What is this clock cycle? It's the clock cycle of the microcontroller. Okay, what we call the bus clock cycle. So just to forget about this, what is bus clock cycle? Take it as a microcontroller clock frequency. So, for example, at 48 megahertz, this is just an example. This is one of the clocks that our microcontroller can work at. Okay, it decrements every 20 0.83 nanoseconds, which is actually 1/48 megahertz. This is 28, I'm sorry, 20, not 20, so 20.8 nanoseconds. Okay. And as I said, we are counting down. So this val here, which is the current count of the counter, actually goes from N to 0. It's not up counter, it's down counter. The sequence is something like this. We start by N, then we go to N-1 after one clock cycle, then N-2 after another clock cycle, and so on until we reach 0. Then what's gonna happen? If you didn't disable the Systick afterwards, okay, it will recount forever. Okay, so it will start again from N. It's like overflow. Start going from N, then N-1 until it reaches 0, and then again N-1 until again it reaches 0. Okay. Systick is a modulo N-1, N+1 counter. That means when you count from N to 0, there is, N+1 counts. So for example, if N equal to 2, we will count from A2, which is N, then 1, then 0. How many counts here? There are 3 counts. That's why it's N+1. Okay, not N. Okay, this is just an overview. So how about the setup? Setup then registers. So we have 3 registers. Okay. The first register is the control register, as I said to you. Let's see in here. This is a control register, so configure or set up Systick Timer. We are very concerned here with 3 bits, basically, or 2 bits. In setup, 2 bits. The enable bit, this should be 1. The clock source, it should be 1. Okay. And here is a flag. You remember, guys, the interrupt flag when there is an interrupt for some board, for example, you have this flag bit that turns from 0 to 1, so that the microcontroller knows that he should do something now, which is the interrupt service routine. It's something very similar. Okay. Actually, Systick can be used as an interrupt as well, as we will see on Monday, tomorrow. Okay. And here is the flag for that. But the flag here is related to the timer. And when it will turn from 0 to 1, when we reach 0. Okay, remember the operation of the Systick, you load some value, which is, for example, N, then it will count from N to 0. When it reaches 0, the flag will turn 1. So you load the load register with N. Then the count will start from N until it reaches 0. At this point, the flag bit turns from 0 to 1. In setup, when you set up the Systick, we deal with registers. We said that you will put 1 here in the enable bit. You will put 1 here in the clock source bit. You put 0 in the flag bit. Why? To ensure that, if you overwrite any, of course, we use the microcontroller all the time. So maybe, for some reason you're using Systick and you forget to reset it or something, then there is 1 there. So you need to be sure that there is 0 there. So when it turns from 0 to 1, you are sure that the count has already reached 0. So some amount of time has already passed. Okay. Here is very simple initialization. So 2 steps. First, the value that you want to count from. And here is some observation for this value. So this is the load register. The load register is actually 32 bits. Also, we are not using all the 32 bits. We are not using only 24 of them. So the maximum value that we can load this register with is 24 bit, 24 ones. Okay. And 24 ones is if 6F. This is the maximum value you can count from, or the maximum delay time, you can say. So in the initialization, this is just an example. You can put any number less than this number. Okay. Then the counter will count from this value to 0. And here is the second step, which is the control register, in which you put 1 here, 1 here, and everything else is 0. So it's a 32-bit register. So 1 at the first bit number 0. Then you put 0 here for this guy, or you don't care about it. Then you put 1 on the second bit, this bit here, and everything else is 0 until 32. So what is this number? This is 5. Okay. Good. So this is setup. One of the applications is to measure the delay time of some module, some part of your code, and you want to measure the delay of this part. That's good. We know that when the timer starts counting, it will count down from some value n, for example, to 0. Good. So here is, for example, the part of your code that you want to measure its execution time. So you want to measure the execution time of that guy. For example, a function, whatever, some part of your code. Here is it's like a function. What you're gonna do is you're gonna read the var register. So you're gonna create a variable. This variable should be 32 bits. Remember from here it's 32 bits. Var register is 32 bits. So you should create here unsigned int 32t variable to hold the current value of the var register. Good. Then this guy will be executed. And after that, so this can be the start time. Then you measure the time again, the current value of val. Okay. So you have another variable which should be again 32 bits. To measure the time after you execute this portion of the code. Okay, so this is the time before execution start. This is the time after execution of the stop. Then you subtract them from each other. And here is, just a bitwise operation. That's it. This is a bitwise operation. To get only the 24 bits that you are interested in. Remember, the maximum value is 24 bits, not 32 bits. That's why we need to make this bitwise operation here with 6 Fs. And remember, we will subtract the stop from start because we are counting down. So the start timer value is larger than the stop timer value. So for example, this may be, if you start from n, this may be, for example, n minus whatever, 1000. Okay, this may be n minus how much? For example, 2000. Okay, so if you measure this, if the time elapsed or the execution time of this part, system under test, is n minus 1000 minus n, and the minus minus will be plus. So this give you n, and how much is this? Plus, I'm sorry, n will go with n, and this will give you 1000. 1000 ticks. 1000 clock cycles. Then if you know the clock cycle, if you know the frequency of your microcontroller, you can know the time of the execution of that line or this function, system under test. Okay, that's good. Now let's take a look at, these three terms here: the precision, resolution, and range. These three characteristics of any timer is related to the clock at which the timer clocks. Okay, so we cannot explain them without referring back to the time, to the frequency of the microcontroller. So for example, at 48 megahertz, okay, we can determine these three characteristics of the timer. First, the precision. We have 24 bits precision. Okay, that means when you have n will go to n minus 1. You cannot have n minus half, for example. That's the precision. Okay, so we have n plus 1 precise values for the timer. That's it. Okay, then if you know the clock frequency, you know these n values or n counts, okay, will give you, each clock will be some value based on the clock frequency. What you can measure, the smallest time that you can measure, is actually 1 clock, right? So 1 clock is the smallest value you can measure, which is 1 over the clock cycle, F clock frequency. In 48 megahertz, it is 20.83 nanoseconds. I mean, if the system under test takes time less than one cycle, you cannot measure it precisely. You will measure it always at 1 cycle, because this is the smallest. How about the maximum? The maximum time is n counts. Okay, so if the system under test takes more than or needs more than n cycles, you will have overflow. So what is the maximum time? It's again related to the clock frequency. Okay, so the clock frequency 48 megahertz here. So to measure the maximum time, you have 6 F's. This is the maximum count multiplied by 20.83 nanoseconds. This will give you 349 milliseconds, approximately milliseconds. So if the system under test takes more time to execution than 349, you will have overflow, because as we said, the count starts from n to 0, then it counts again from n to 0. It will not stop. So you will measure any correct value. Okay. Good. So another application is system timer wait. Sometimes, lots of times, as we saw previously. Okay, each week we take some lecture, we take some code and we needed this dummy for loop to make a delay. Also, it's not a precise, it's a very dumb, way, but it creates a delay. But it's not measurable. We don't know if we count from 1 to 1 million, how much time is this exactly? Okay. So one of the application of Systick is to do that, to create a delay with a precise time that you want. Okay. So we said that you load the timer, then it will count from the value to 0, and which when at the time it reaches 0, the flag will turn 1. Okay. So if you check this flag, you know if the delay, if you finished counting or not. Okay. So for example, so I think there is example here. Yeah. So we can just go to this example here because it's more precise. Oh yeah, no, it's the same. Okay. So for example, at 48 megahertz, if 48 megahertz, okay, if we load the timer with 6F, so n equal to this one, okay, so it will start counting until it reaches 0, and when it reaches 0, then the flag will be 1. And how much time is this? This is this number multiplied by 1 over 48 megahertz, which this time here is actually the clock cycle time, T clock, which is 1 over F clock. And this is 349 milliseconds approximately. Okay. So if you want to create 349 millisecond delay, you can use this one, this piece of code here. And remember, you check the 5th bit, which is the flag bit. If we go back, let me go back here to show you. Yeah. So this is the flag bit. It's bit number 16. I'm sorry, bit number 16 from 0. And when you count, when you have a hexadecimal number, if you go back to here, if you have a hexadecimal number, so this is 4 bits, 4 bits, 4 bits, 4 bits, and here is the 5th 4 bits. So the first bit here will be bit number 16. Okay. Good. So yeah, if here he's counting from n minus 1, that's that's not that bad. Okay, and I mean it doesn't really matter a lot. So, but it's a safer way not to have overflow. Okay, so it doesn't work obviously for n equal to 0 because it will give you -1, which is very bad, or n equal to 1, which will give you 0, so you will not count anything. So avoid these two values. Okay. Now, if you want to generate, delay more than the maximum that you have. Okay, so for example, 1 second. So let's go back here. The maximum delay here is 349 milliseconds. How about if you want 1 second? What are you gonna do? Okay, one way, it's not so accurate, but one way is to make a loop. So loop like this. Let's for I equal to 0 until 2 I plus plus. So this part will be repeated 3 times, right? 3 times, then you will count 349 3 times, which is around 1000 plus something, right? 1000 millisecond plus 47 milliseconds. So 1047 milliseconds. Okay, it's approximately equal to 1000. So, but this will give you an idea how to do it. So don't create a delay here in between for 348.49 milliseconds. Make it, for example, 100 milliseconds. So of course, now we will count not for the full, but for some value, some n, which is of course not 6 f's, which is the maximum value, but some value of n that will give you 100 milliseconds. Okay, so here is an example for it. Okay, 48 cycles means 1 microseconds. Basically, it's very simple. 48 cycles multiplied by 148 megahertz, which is 10 to the power 6. This guy will go with this guy. So 1 over 10 to the power 6 is actually 1 microsecond. Good. So 48,000 cycles we will multiply, will give you a time, which is 1000 this time. So 1000 multiplied by 1 microsecond is 1 millisecond. How about if we want 10 milliseconds? So 10 milliseconds, then multiply again this number by 10, or this number, I'm sorry, by 10. So it will be 480,000 cycles. This will give you 10 milliseconds. So you will make a delay here, okay, and you make a for loop with 10 times from 0 to whatever you want. Here it should be 10, and for each time, so this should be 10 in that example. For that example, should be 10, and each time you call another part of the code, which is actually this part, you call it, okay, which will create one, which will create what? Which will create 10 milliseconds. Actually, he's, yeah. This should be 1 millisecond. This is a general also. So. Actually, he should be, he should put here the minimum. But anyways, that's not, that's not. So that's even more general. Okay, so this is alone will create 10 milliseconds. This is 10 milliseconds. Then, according to the delay, for example, if it's 100, this will give you 100 multiplied by 10 milliseconds, which is 1000 millisecond, which is 1 second. Okay, that's even general. If it's just 1, this will give you 10 milliseconds exactly. Okay, so that's even more general. Okay, so here is a summary of this. Okay, basically you can measure till this moment. You can measure, the elapsed time of part of the program, which barely we will use this. Okay, but our main application will be to measure, or to create a software delay. Okay, a delay in the code. And tomorrow on Monday, the first thing that we're gonna do is actually using this to create or to light or blink the LED one as usual. Okay, every 1 second. So 1 second on, 1 second off, 1 second on, 1 second off, and so on. Okay, so we're gonna use this. The first thing that we're gonna do tomorrow on Monday is to code this program to blink the lid. Then we're gonna explore the second and most important application of Systick, which is the pulse width modulation to control the speed of the motor. Okay, guys, see you tomorrow. Bye-bye.